Hi everyone, in this video we'll be discussing the problem check mirror in N-ary tree. Basically in this problem you'll be given two N-ary trees and you have to check whether those two N-ary trees are mirror images of each other or not. Now what is an N-ary tree? So an N-ary tree is a tree where a particular node can have more than two or more children, right? So basically it can have many children. Like if I discuss this case, so for this tree, like let's say it has many children, right? Like this. So it can have many children, like it can have 7 as well. So this is what the definition of N-ary tree is. So basically the problem is saying that you will be given two N-ary trees and you have to tell whether the trees are mirror images of each other or not. Like they will be giving you input in a specific format. So what they let's say the first array that they give you is 1 2, then 1 and 3, and the second they give you is 1 3, 1 and 2, right? They give you first array as 1 2, 1 and 3. So what you will be doing is 1 will be connected to 2. Like if you discuss, so for 1 its left child will be 2, then this one will be connected to this 3, then 1 here, since 3 is given earlier. So basically you will be having the parent and child relationship u to b, like for this and this, and similarly for this and this. So 1 comma 3, so basically 1 will be connected to this 3 and then 1 will be connected to this 2, right? So now you can see that these two are mirror images of each other. If you apply a mirror in between, so you can see that these two will be a mirror image of each other. So you'll write it true for this particular case. But let's say if you were given a case like this, let's say if you were given a case where you have been given 1 comma 2, 1 comma 3, so in that case what you would have drawn is 1 is connected to 2 and 1 is connected to 3, right? So in this case you can see that these two are not mirror images of each other, so you would have written a no or 0 for this case, right? So now let's discuss another case for this particular problem. Let's say, first of all, let's draw the tree and see how actually the input will be. So let's say 1 is connected to 2, then let's say 2 is connected to 3, and then let's say 2 is connected to 4 and 5, right? Like this. So in this particular case, the array that will be given to you will be like this: 1 2, then 1 3, then you will be given 2 4 and 2 5, like this. Basically, first of all you will take this particular relationship, then this, and then this, and then this, right? So this is what will be given to you. And now let's suppose that the another one is also given to you. So let's say the second tree is given to you as 1 3, then 2, and let's say it is given as 5 and 4, right? So in this particular case, as we discussed, that it will be nothing but 1 2, then 1 3, and then 2 4, and then 2 5, right? This will be the case. For the second case, it will be 1 3, then 1 2, right? Then 2 5 and 2 4. Now you can see that these two are actually mirror images of each other, because if you apply a mirror in between, so you can see that if you will apply a mirror on each other, so they can you can easily observe that this will come out to be mirror images of each other. Now why is that so? So if you will observe clearly, so let's take a simpler case and try to understand that what actually is being done in this case. So let's say if you had a tree like this: 1 was connected to 2, 2 was connected to 3, and let's say this was the case. And let's say another case was like this: 1 4 and 3 and 2, like, right? So in this particular case, actually you cannot see the tree and you have to tell the answer using the arrays, right? So 1 2, then you have been given 1 2, that is the first UVH, then 1 3 and 1 4. Secondly, you have been given 1 4, 1 3 and 1 2, right? So in this case, how is it possible? So basically if you observe this thing, so you can see that in the first case the edges are 1 2 1 4 and 1 2 1 3 and 1 4. And in the if you need to have a mirror image, so basically you should have 1 4, then 1 3 and then 1 2, right? So the last that is coming out here, the last u comma v edge that you have there, it should be the very first, right? So can you think of a data structure that can help us? Maybe you cannot, right? Currently you cannot, but let's say if I give you something like let's say geeks, right? So if I give you a string like geeks, and let's say, let me make this g as a small. So if I make this g as a small and I tell you that okay, this geeks is given to you, so what you can understand is that if I give you this geeks and I give you this another string that is this, right? So you will say that are these two mirror images of each other? Yes, these two are mirror images of each other. Why? Because if you will apply a mirror, so you can see that with this s, then this k, and two e's, and then g, right? So how can you check that? So you can see that this particular string got actually reversed, right? So basically you can see that you have to apply a data structure in such a way that the first h pair that you are taking here, it has to be seen as the last, right? Then only it will be the mirror image. Basically the first character that you are taking here, it will be the last there, right? So similar kind of objective you want to have. So basically the first character that is coming for me, or the first pair of u comma vh that you give me, it I want it to get to be last, right? So that's why I can think of a data structure that is stack, which applies the concept of last in and first out. Basically the h u comma v pair that I am getting, that is coming first, I want to check it at the last for a particular like for one specifically. If you give me, so for one, the very first edge that I have is what? For one, the very first edge that I am getting is 2, then the next edge I am getting is 3, then the next edge I am getting is 4. So what I want to check in this particular answer, if I want to see, so what do I want to check? I want to check first of all that 1 is connected to 4 or not, right? Then I want to check that whether 1 is connected to 3 or not, right? Similarly, I want to check that whether 1 is connected to 2 or not, right? And if it is so, then in that case what I'll do is I'll definitely return a yes or a true in this case, otherwise I'll return a false. So basically that is why I'm using a stack. And now for storing this thing, that is the edges, what I can do is I can use the map. So basically every edge can behave like a map. So I can make a map of, let's say, int comma stack, right? So for every edge, like for one, I'll have a stack that will store all the relation of edges. Like if you give me this, as I told you, 1 2 3 and 4, if you give me this, then it will be stored in 2 3 4. And let's say if you give me the second tree as 1, then 3, then 2, and then 4. Let's say if you give me not this, but if you actually give me a structure like this, 1 4 and then 1 2 and then 1 3, right? So in this case you can observe that the edges that you will be giving me here, initially I'll get 1 2, then 1 3 and then 1 4, right? Right, this thing you will give me. But what I have in the second tree, I have 1 4 1 2 and 1 3, right? So in this case, if I'll compare it in the map, so I can see that, okay, for one, the very first edge that I have is 4, so that's what I have. So I'll pop it out, right? After this, after 4 is being popped out, so I'll check what is the next edge. So I can see that in the tree that's been given to me, in the second tree, I have the h2, right? For one I have the h2, but I don't have it, right? So that's why I'll return a false for this particular case, right? I'll return 0 or false for this particular case. So that is how I'll be approaching this particular problem. So basically you had to identify that which particular data structure you will use for solving this kind of a problem, and we can easily see that we'll use the stack data structure that uses the concept of last in first out, because the edge like that's coming very first for you, like as I told you, let me remind you this. So if I take this particular example again and this particular example, so you can see that in this case what will happen, the edge will be 1 comma 2, then 1 comma 3 and then 1 comma 4, right? And in this 1 comma 4, then 1 comma 3 and then 1 comma 2, right? So this will be the case. So in this case you can see the edge relation that is coming first, the relation that I'm having here first, it will be the last here, right? For each and every edge. So that's why I'll be using a stack data structure. Now let's quickly move to the code implementation of this particular problem. So in this particular problem, what I'll be having is, I'll be making a map that will help me to store all the things. So basically I can have an unordered map I can have, and in that unordered map, for every edge I'll be storing the stack of edges that with which it is connected to, right? And let's say I name it as nothing but MP, as we usually do, right? So in this case what I'll be doing is, let's say I start I from 0. So basically I will be starting from 0, and I will be less than 2 cross e that has been given to me, basically the number of edges. And since I told you that every ith edge that I have, like in this case, let me come to this part and explain you. So for every edge that I have, let's say this is the ith edge, right? So for this is the I plus 1th is the connection, right? Then similarly, for if this is the ith, then this is I plus 1th, right? So I'll be jumping in terms of 2. First of all, this will be my I, then this will be my I, right? So every time I'll be taking jumps of 2. So I plus is equal to nothing but 2, right? I plus is equal to 2 I'll do. And then what I'll do is I'll simply insert all the things into the map. So I'll say map of nothing but a of I. Basically for the current edge, let's say for the edge 1, if you give me 1 2 3 1 2 1 2 1 1 2, then 1 3 and 1 4, so I'll be inserting them one by one. So I'll simply say that map of a of I dot push nothing but a of I plus 1, right? So I'll be pushing the next. Now I have to take the jumps of 2, as I've already told you. So for every edge I'll be storing, for every u I'll be storing the corresponding v to it, right? Then next up, as I told you, I'll be checking in the second tree. So I'll start my iteration in the second tree. So I starts from 0, I is lesser than nothing but 2 cross e, and then I'll as I told you, I'll be doing I plus is equal to 2. Why? Because for every pair I'm having this kind of a relationship, right? So Then next up, once I have done this, so what I'll do is I'll check that if my map of b of I, right, b of I, that is for, let's say for 1, let's say if you have given me this thing, let's try and have this example. So if you give me 1, if initially I have stored for 1, I've stored in this order, that is 2, 3 and 4. And if you tell me, that for 1, if you tell me, so if you give me the mirror tree as 4, 3 and 2, so what I want is, in the stack, if I have stored, so in the stack I have stored since, so it will be nothing but 432, it will be stored in this format. And the second tree is this, nothing but 432, right? So I'll check that if for the in the map, if I do not have that same relation, then in that case it will not be a mirror tree, as I've already discussed, right? So if map of bi dot top, that is the topmost element of the stack for that particular node, if for that particular node, if it is not equal to b of I plus 1, right, if it is not equal to b of I plus 1, in that case I can simply return a 0, or you can say false. In that case I can simply return 0. Otherwise what I'll do is I'll simply keep on popping this particular edge. Why? Because if, let's say, I was given 1 with respect to 1, if I had stored in the reverse order in the stack, that is 4, 3 and 2, so and you give me the edges in this order, that is 4, then 3 and then 2. So since I want to check that, since I have already covered this edge 4, now I want to check with 3, so that's why I have to pop this 4 out from the stack, so that I can check it with 3 and then I can check it with 2. So every time I'm able to check and it is I'm finding it correct, so I'll keep on popping those edges, right, so that I can keep on checking and I can apply this particular last in first out concept, right, so that I can check the mirror tree. Now I'll pop this particular relation out, u comma b, and then similarly in the end what I'll do is I'll simply return a 1, that will indicate true that this particular tree is both the trees are having a mirror image, right? Both are mirror images of each other. Now let's try and compile this particular code and see whether we have any issues or it is getting compiled. So we are having any issue. So yes, I have not declared I. So in the second case, I will be declaring I. Let's try and compile it and see whether it's working or not. So for this case, you can see that it's giving a 1. Let's try and submit this code and see whether it's working or not. So you can see that it got accepted. So thank you for watching this particular video, and in case if you have any doubts, so you can mention that in the comments and I'll reply back as soon as possible. Thank you.